Good morning, Professor Zhang and Professor Sun. It is my pleasure to share my recent work on our conference. At first, I want to introduce myself briefly. I am Chen Jiahui, and I come from Northwest Polytechnical University in Xi'an, China. And my topic today is study on the material transport of aluminum droplet evaporation under convection conditions. The background of my study is about solid rocket model. It also can call SRM. SRM contains about 4 parts. The first one is about the motor casing. Casing is here, and in the casing is propellant. And this one is igniter, and this one is a nozzle. The SRM works at high pressure and high temperature. The pressure of the combustion chamber is about 10 million Pascal, and the temperature of the combustion chamber is about 3,600 kilometers. In order to obtain more energy and to suppress the combustion instability, we usually add metal particles into propellant, such as aluminum. At such a high pressure and temperature conditions, the metal particles will become the droplet. So, study the droplet evaporation is one important part of the metal combustion. Usually, we study the droplet evaporation at the still conditions, not the convection conditions. In still conditions, we use some one-dimensional model to study it. We found that the droplet evaporation is ruled by the D square law. D square law is the evaporation time. It's proper to the diameter square of the diameter, and this one is a constant. We usually call it as evaporation constant. Some researchers found that for the aluminum particles will generate the oxide cap, and this law may be not square. It's about 1.8. The rest is the same to the droplet evaporation. In this study, we want to study the mixing of the vapor generated from the surface of the aluminum droplet and the gas with high velocity. So we want to use the LCS, which is Lagrangian coherent structures, and the tool to study the mixture of the vapor and the gas. The definition of LCS is the largest stretching or compressing of metal surface in flow field with luminant time. And this is some case to illustrate that what is the LCS. This work made by George Hiller. And the LCS has a very good property that the maximum compression or stretching of the material surface can prevent the flow from passing through the material surface, which forms a transport barrier in the flow. And this is our model. This one is an aluminum droplet, and the aluminum droplet in high pressure, it will evaporation and generate the aluminum vapor. And this is a coming flow. It's about high temperature and high pressure gas. For our study, the evaporation time is very short. It's about 0.1 seconds, and the flow past the droplet cause more short time. It's about 0.001 seconds. So we can assume that the volume change, the volume is not changed. So it's this assumption. The other two assumption is we assume the reaction is negligible. So we only focus the evaporation of the droplet, and the other one is the values of evaporation constant are equal. It means all of these are equal. This is our mesh, and this part is the mass flow inlet of the gas. The mass flow rate is about 0.4 kilogram per second. And this one, and this one is the outlet. And the environment, the temperature of the environment is about 2,800 Kelvin, and the pressure is 1 million Pascal. The droplet, we calculate two cases. The first one, the mass flow rate is larger. It's about 0.785 kilogram per second, and the second one is very late. This is our results. We can see the flow is periodic, and this is a coming flow, and this one is a weak. We can see the vortex generated periodically. The flow field is like the Kalman vortex street. And then we calculated the finite time Lyapunov exponent field of this case, and we obtained the LCS. The first page, this page is about attracting LCS. Attracting LCS use the past the past information, and we can see in front of the droplet there are strong LCS here. It means a strong transport barrier. The transport barrier is the strong transfer barrier here, and we can see it exists all the period. It prevents the vapor and the gas mixing. And we can see the vapor generated generated at the surface of the droplet will enter the wick through the tunnel made by the attracting LCS. It will go this tunnel into this channel into the wick region. And this one is the repelling LCS. Repelling LCS use the future time. We can see the coming flow can enter to the wick region through the tunnel made by the repelling LCS. Here, 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 and here. So combine the attracting LCS and the repelling LCS, we can obtain 4 conclusions. The first one is there is a strong transfer barrier in front of the droplet, preventing the mixing of helium vapor and gas. The second one is the helium vapor entering the wick through the channel composes of the attracting material line periodically. The second one is the same. It's about the gas, hot gas entering the wick. The last one is the mixing of helium vapor and gas happens in the wick of droplet. Thanks for your attention.